Hello, we are discussing about GATE 2004 ECE paper, and the topic we are discussing is electron devices. This is first 2 mark question, came in 2004 GATE. In abrupt PN junction, the doping concentrations on the P side and N side are Na is equal to 9 into 10 power 16 per centimeter cube and Nd is equal to 1 into 10 power 16 per centimeter cube respectively. The PN junction is reverse biased and the total depletion width is 3 micrometer. The depletion width on the P side is A 2.7 micrometers, B 0.3 micrometers, C 2.25 micrometers, D 0.75 micrometers. Given abrupt PN junction and doping on P side, that is nothing but acceptor concentration, which is Na, is given as 9 into 10 power 16, and doping on N side, which is donor concentration, that is Nd, given as 1 into 10 power 16 per centimeter cube, and the PN junction is under reverse bias. By that time the total depletion width is 3 micrometer. Now how much is the width on P side? The correct answer for this question is B 0.3 micrometers. We will see the details now. So whenever we are going with a PN junction, for PN junction under open circuit, there is a built-in potential barrier formed. That potential barrier formed is also called as depletion region, transition region, or space charge region. This is which is consisting of ions, positive ions on N side and negative ions on P side. So the depletion region consisting of positive ions on N side and negative ions on P side, and over which the ions are distributed, that is treated as width of depletion region W. So this is total width of depletion region. If you are only considering on P side, it will be Wp. If you are considering the number of ions on N side, the width is treated as Wn. So total width W is equal to Wn plus Wp. So in the depletion region, number of positive ions on N side is exactly equal to number of negative ions on P side. So positive ions on N side is nothing but negative ions on P side. So in other words, we can write charge on N side is equal to charge on P side. Charge on N side implies nothing but this total block. So in this block, only in this depletion region positive ions are there, and other region N-type semiconductor, which is extrinsic semiconductor, which is electrically neutral. So total charge is nothing but charge in depletion region only. Total charge in P side is nothing but charge in depletion region of P side. So both are going to be statements same. Charge on N side is equal to charge on P side. So how do we charge? Charge is nothing but volume charged into volume of that side. So for N side, this is rho Vn is nothing but volume charge density on N side into volume of N side. Charge on P side, volume charge of P side into volume of P side. Charge density is nothing but Q times of Nd for N type, Q times of Na for P type. Volume is nothing but we will calculate like this. If you assume the PN junction under 3 dimension, by that time this side is nothing but it is area. The area is going to be common for all. If you are going to draw a lines like this, at that time that also considered as area. Area is common for N side as well as P side. So that area into Wn will become volume on N side, area into Wp will become volume on P side. So we are writing Qnd into area into Wn is equal to Qna into area into Wp. From that one we are arriving one conclusion. Nd into Wn is equal to Na into Wp. So this is the relation between doping concentration and width of depletion region. Nd into Wn is equal to Na into Wp. From this one we are going to solve the problem. For the given question, the data given is Na is equal to acceptor concentration is 9 into 10 power 16 per centimeter cube. Donor concentration 1 into 10 power 16 per centimeter cube, whereas total depletion layer width is 3 micrometers, which you can write it as Wn plus Wp. In depletion region, just now we have seen Na into Wp is equal to Nd into Wn. Substitute the values. 9 into 10 power 16 into Wp is equal to 1 into 10 power 16 into Wn. From that one we can say Wn is equal to 9 types of Wp. We can write the total depletion layer width as W is equal to Wn plus Wp, whereas Wn can be replaced with 9 Wp. So total width is nothing but 10 times of Wp, which is nothing but 3 micrometer. So Wp is equal to 3 by 10 micrometers, which is nothing but 0.3 micrometer. So the width of depletion region is 0.3 micrometers. Actually, from this question we can conclude one important point. From this Na into Wp is equal to Nd into Wn. If the doping concentration on p side and n side are equal, by that time Na is equal to Nd, then Wp is equal to Wn. So if p and n sides are equally doped, the depletion region also penetrates equally in both sides. If one of the side is going to be heavily doped, then the width of depletion region is penetrated into lightly doped side. So look at this one. Out in this question, Na is heavily doped compared to Nd. Na is 9 times more compared to Nd. So that p side is heavily doped. That's why width of p side is very small, whereas width of depletion region on n side is very large. So this is width of p side is 0.3 micrometers out of total is 3 micrometer. So width of n side is nothing but 3 minus 0.3, that is 2.7 micrometers. Always depletion region penetrates more into lightly doped side than heavily doped side. So for the given question, the correct answer is 0.3 micrometers. The option is B. Thank you.